Hello, and welcome to today's Saratech enablement session. My name is Andrea Hall, and I'm the Customer Relationship Manager here at Saratech, and I'll be your host today. Presenting today, we have Daniel DeLong, Leong, and he is an applications engineer for Markforged, and we are just lucky enough to be such great partners with Markforged, and he is going to be talking to you today about making strong 3D printed parts with effective fiber reinforcement. So we are looking forward to today's presentation. And our sessions run about 30 minutes each. If you haven't attended one of our sessions before, they are all recorded and they are posted to our Saratech YouTube channel. Make sure you go ahead and check out our YouTube channel. You'll be able to see all of our past sessions there, all of the recordings. And we will also be sending out the recording for today's session. And then next slide. So just a reminder, this is an open forum. So if you have any questions or comments during the presentation, you can go ahead and type them into the questions box over on the right-hand side, and I will just kindly interrupt Daniel and let him know what your questions or comments are. We will also leave some time at the end for questions and comments because we did see that there were quite a few upon registration. So this presentation will probably be around 20 minutes or so, and then we're going to leave some time there at the end. So make sure that you keep your questions and comments ready, and we will be able to discuss those towards the end. And with that, I'm going to pass the baton over to you, Daniel.
All right, hello everyone. My name is Daniel. I've worked at Markforged for about 3 years, so we've only been at the company for about 6 years, so it's been a while. I do what's called application engineering here. Basically, my background is mechanical engineering, and since we make 3D printers, and 3D printers are kind of a new way to fabricate parts and don't have as many established standards, a lot of what I do is kind of focusing on figuring out how to leverage the technology that we've kind of brought to the market in ways that are productive for you, the customers, or you, the people who are looking at integrating 3D printing. So what our kind of original unique calling card is continuous fiber. So what that means is basically in your typical plastic prints, you'll see a normal kind of like whatever a thermoplastic part, whether that be like a PLA or an ABS or a nylon. And what we do is in augmenting that, we put continuous fibers in the part. So it adds a ton of interesting different design requirements and kind of ways to go about reinforcing a part that are even above the typical design for 3D printing. So in this webinar, what I'm going to talk about is kind of how you can leverage our platform and ways you can leverage our platform in a bit more of a hands-on way to reinforce your parts, to get stronger parts, and to figure out how to design parts for a fiber reinforcement thing. So with that, I'm going to talk through kind of 4 main topics and then leave a bunch of time for questions if I can. So the first one is kind of talking through the platform I just very briefly described. The second one is from our perspective, what are the options? So what are the dials you can turn in our software, Eiger, to actually reinforce parts? The next one is kind of on a little bit of a broader scale. With those dials, what can you do from a strategy perspective? So what are some regimes you can do to reinforce parts? And then the last thing I want to talk about is just kind of go through like a case study or a quick workflow of if I have a part, how I would go about thinking about reinforcing with fiber. It's like a 5-step process. It's pretty simple, and it kind of gets you from thinking, why would I ever think about putting fibers in my parts, to, oh, this is the way I would do it. So I guess with that, why reinforce with continuous fiber? So I got into it a bit, but if you look at these like really cool radar charts that someone on our team built, the leftmost one is kind of how you would evaluate nylon as a material. So nylon is really chemically resistant and really durable. You can beat it up and it will usually stay together. It won't break apart. But it's not super strong and it's really not stiff. And from a heat resistance perspective, it has basically a really like high melting point, but it's so ductile that the heat resistance is actually not high, because the moment you heat it up, it'll bend. When our plastic itself, we don't print with pure nylon nearly as much as we print what we call filled carbon fiber nylon. And so that has chopped carbon fiber inside of it. And what that does to the nylon is it just basically makes it a little bit better. It makes it stronger and stiffer, and it all of a sudden has heat resistance because it won't bend as much. And the print quality is really high. So that's from a Markforged perspective, our base thermoplastic. But even comparing to that, the reason why continuous fiber is valuable is if you look over on the rightmost thing, I love the person who made this chart because it's just like, why would you make the chart if it's so large? But the idea is that what continuous fiber enables you to do is in the scheme of plastic 3D printing, kind of have a part that you're printing as if it's plastic, but that has properties that far supersede any type of traditional plastic you know about, especially from a strength perspective where the continuous fibers yield a composite part that's really strong, to a stiffness perspective where they don't give, and a durability perspective where you really can do all kinds of stuff with them and put them in places where typically plastic parts would not go. So this is kind of a basic two-line reason. It boosts your material properties, and they on the high end can even replace metal or aluminum components depending on the loading conditions and among other things. So how does it work? I mentioned it a bit before, but the plastic, we have two nozzles on all of our printers. The plastic matrix is printed by one of the nozzle. It kind of creates the part's exterior shape. So if you look at this part on the right, it kind of looks like a normal 3D printed part. In this case, it's a rubber jaw. But what happens is you have internal fiber, you have fiber reinforcement inside of it. So these lines inside the part are unique layers of continuous fibers. And so what that does is that basically gives you that kind of like skeleton to a plastic part that you wouldn't normally expect, and that's what adds all that strength. So it's printed layer by layer, but those layers have continuous strands of fiber, and that's the key differentiator there. Cool. And so what's the result? So the result is strong parts. And so we like to break parts into kind of three kind of base groups as to what they are. They're usually something, either a prototype, a tool or a fixture, or an end-use part. And this part over on the right is something I like to call out as just a particular example of what the fiber printing can do for you. This is a Trump press brake. It's used to form, obviously, steel. This is a job shop in South Carolina that owns one of our printers, and they basically had kind of one of those what if moments as to whether or not they could print basically a metal forming device for 14 gauge steel. And they tried it, and they put fiber inside of it, and lo and behold, it just worked. So this is that actual press brake in action. So I think you can hopefully see my cursor. This part here and this part here are both printed with fiber reinforcement, and the fiber reinforcement enables them to punch out but form like basically dimples or divots in this steel part. So that's one of many examples in that kind of strong parts area where we're seeing specifically the most advantage. So that's the value. But now what dials you can turn. So at its core, there's two kind of options we present for filling with fiber. There's concentric reinforcement and isotropic reinforcement. And so in our software, those are the options you can select. So on the concentric side, what it's doing is this is a slice of a part, basically, just for reference. This is a two-dimensional slice of a part. If you look, the black coloring on the outside here is the exterior or the wall of the part. These gray triangles are the infill of the part. So that's basically like anywhere with most 3D printed parts. It's not solid. It's basically a hollow infill. Ours are no different. And then if you look, the differentiator here is on each of these, you'll see kind of blue lines around the outside of the part. This is basically continuous carbon fiber strands wrapping around the edges of the part. And so in the realm of concentric fiber, we kind of provide three options. We have basically outer walls, in which it takes the outer wall of your layer and puts loops of fiber around it. We have inner holes, which is the one in the middle, where you basically reinforce either like a bearing press or a post hole or something like that that's going through your part. Or we have all walls, which is my personal favorite, which is basically you reinforce both. And so if you look here, if you look kind of closely at these fiber paths, you can actually see that it is actually only one string of fiber, even though it's multiple on the outside of each part. And you can see it kind of there's a point on the left side of each of these cross sections where you can see the fiber kind of go in from one ring to the second ring. So it is one strand of fiber, and that's what provides that strength. All right. And so then the other option here is isotropic. And isotropic is basically you start with concentric rings around all those critical holes, but then instead of leaving the rest of the part as if it was normal infill, you put just basically zigzags of fiber in each part. So if you look at the part on the left, again, it's a cross section. you start with that normal kind of wall structure, and then the rings of fiber on the inside, and then you have these zigzags. And what it's used for is to provide more unidirectional strength. So if I'm pulling in one direction or bending about one direction, it's very strong. In other directions, it's weak. So you can leverage this in a number of ways. The default way that Markforged does it is that we basically alternate the direction of those zigzags on each layer. So if you look at the graphic on the right, you'll see that basically in our typical place, you have the fiber all basically change by 45 degrees, rotate by 45 degrees each layer, and it kind of repeats itself. So you get what we would call a quasi-isotropic part, or something where basically in the XY plane or in the plane parallel to the build plate, you have long strands of fiber going in each direction. And so it costs more money because you have to put more fiber inside the part, but it's a good way to fill an entire layer. So within these two, the things you can control, so you can control on a layer by layer basis whether or not you're putting fiber in, and in that same respect, the number of rings of fiber. So the rings of fiber, if you go back 2 slides, that's just 2 rings. You can put as many rings as will fit inside the part here. So you could put 10 rings if you wanted to. You could put 1, and so that's and that works for both concentric and isotropic. And then on isotropic, you can actually control those angles. As I mentioned, the one that's currently programmed, or the base program, the kind of default is it's programmed to do kind of rotate 45 degrees every layer. But if you wanted to rotate 90 degrees, or you wanted to rotate 0 and just have the same orientation on each layer, you can also do that. So those are kind of the key dials you can turn. Now, when you turn those, you get it to kind of 4 basic reinforcement strategies that are usable in a day-to-day basis, that are things that are kind of worth working with. The sandwich panels, stripes, shells, and then something we call selective reinforcement. Sandwich panels are the simplest. So if you look at this part here on the right, what we're basically saying is reinforce the topmost and bottommost important layers of the part. This is something that we kind of borrow from conventional carbon fiber layups and other things, where they'll build structures out of structures in which they have kind of an internal matrix, and then have the layers of carbon fiber on the top and the bottom. And so what that's doing is it's really good about resisting your bending and XY tension. You can do it with either isotropic or concentric fill, both work. And its strength is that you're minimizing the fiber use, and the fiber is difficult to put in parts from a cost perspective. It just costs more money, while maximizing your utility. As you put fiber close to the center of the part, you're getting less from a bending perspective. So when we default, anytime you basically default reinforce a part, it's going to try to sandwich panel it. And so that's kind of the really good base method for that. The next one is striping. So striping and sandwich paneling are very similar. The only thing is that you add basically basically repeated regions of fiber, as opposed to just on the top and bottom. And that basically, it'll add a little bit of strength, and it'll also combat torsion by putting more fiber in the part. So you have basically specific regions of fiber doesn't like bending in any direction, and it'll make the part a little bit better. But as I said, the closer you get to the middle of the part when you're adding these layers, you get diminishing returns. So striping is kind of a more niche use case, but it is kind of the evolution of sandwich panels. The next one, which is kind of the one that I prefer using if I'm trying to reinforce any parts, is called shelling. So shelling, like you would kind of expect and like you would see from a CAD perspective, is basically taking every exterior surface of the part and reinforcing it, whether that be kind of a roof or a floor on the top and bottom, or a wall on the side. And so the way you do this is basically on layers where there's roofs. So on this part, there's kind of multiple roofs. There's ones here, if you can see my cursor, and here at different layers. You would put isotropic fill, or try to fill as much of the layer as possible, as a sandwich panel, or basically creating a sandwich panel. And then in addition to that, you would then put on the walls of the part where there is less, where you don't need to put those full panels, you'd maybe put 1 or 2 rings around the very outside. And so what that basically creates is kind of obviously a shell of fiber on the outside of the part. And for most perspectives, it's kind of the closest we get to having an isotropic part, a part that acts the same in every direction. Obviously, you still can't pull apart like normal to the layer lines, but you can get pretty close. And so if you're trying to get fiber strength, this is kind of what we recommend, because you don't have to put fiber in the entire part, which is kind of again diminishing returns, but you're getting an extra thing, which is like if you're bending it about the z-axis, the sandwich paneling will not hold up in a way that shells would. Yeah. So and then the last one, so this is again kind of a detail of the shell here, where you see that you have these sections here where you have isotropic panels for these kind of critical horizontal layers, and then you have your concentric where it's mostly just inside the part volume. And combining that kind of minimizes your fiber use while maximizing your utility. Cool. And then the last one we'll talk about is selective reinforcement. So selective reinforcement is kind of a broad area. It's what we kind of describe when you're trying to basically creatively reinforce certain aspects of parts. We often see it if you have a certain feature on a certain set of layers that needs to be reinforced, or you need to basically put fiber in a rib. So the top example is something like a propeller, or some kind of roughly like triangular shaped thing in which they've alternated the direction of the fiber such that each layer goes basically reinforces parallel to the axis of one of those tines. So the first one is the kind of front left one, the second one is the far right one, and the third one is obviously in the back left. You can't quite see it. So that's one way to say, okay, well, if I have this like propeller or say like something looks like that, and I want each blade to be reinforced, I can do it this way. Then the bottom one's a different example where someone would kind of CAD a rib into the part, and then they would use a concentric fill here to create basically a really strong rib in the part that basically resists bending in a way that like basically having a normal triangular or diamond-shaped part would not. So that's another creative way to put parts where you can kind of alter the design a bit to game the fiber algorithm per se to get more reinforcement in a part. Cool. So those are kind of the key things there. If anyone has any questions, feel free to ask now. I have some more stuff, but if you have any questions about those, I'm happy to answer now or later. I don't see any right now, but I'll go on and we'll kind of get to some at the end, hopefully. Cool. So then moving on from there, the last thing I wanted to talk through today was what we describe as the fiber reinforcement method. So when we go through kind of the process of reinforcing parts here, and when we kind of advise our customers to do it, we kind of have 5 discrete steps. We say before you say you click print, we want you to do these things. So the steps are listed here, and we'll kind of get into them. But it goes from kind of identifying what's actually happening to the part when it's in operation to like making sure the fiber works. So the first step, as I just said, is kind of identify your loading conditions. So with any part you're making, especially if you're trying to reinforce it or make it strong, it's obviously being loaded in some way, shape, or form. So the short of this is that you really want to resolve your forces here. So you want tensile, flexural, and compressive forces. Occasionally there's a torsional force as well. But figure out basically how your part's being loaded. So this example part here, we have a nice handy free body diagram where we see that it's kind of being loaded from right to left, and then it's bolted down, so there's counteracting forces everywhere. It also looks, because it's kind of a part with an interesting surface, that it's kind of being loaded into that surface. So there's some basically some loads orthogonal to the plane or that surface. So a couple kind of an interesting little loading condition here, and then and so now that we've kind of diagnosed this, we have kind of a good starting point to say, okay, well, what can we make stronger with fiber here? What would fail if this was kind of a weak, like a normal, like weaker plastic part? So the second thing is to determine how you're going to print it. So as I mentioned, and you can really, as printing is kind of almost any type of 3D printing is a process where you take a part and slice it into layers. Anything that you're doing on a print is usually a 2D operation. So just like that, you can only put fiber in discrete layers, and the layers are always parallel to the build plane. So selecting what face you want to be parallel to the build plane, it basically kind of determines what orientation you're going to put fibers in. So aligning those key forces parallel to the plane is kind of your best move. As I kind of mentioned offhand earlier, our parts are weakest when you're pulling them in the axis that is orthogonal or perpendicular to the build plate, kind of pulling them apart on those layer lines, and the fiber will not make it any stronger in that respect. So you want to avoid forces there and kind of get all your forces in the plane parallel to the build plate. So bending forces especially is really important there. Yeah, so once you've decided your print orientation, the next step is to figure out where you're going to reinforce. So if we go back to our free body diagram, you can see here, it's bolted down here and there's some reactive forces, but it looks like the primary force that we care about is right in this range. It looks like, I'm not actually sure exactly what this part is, but it's something that's holding something else that's getting loaded down on that surface here, which resolves into that force. So in that case, the thing that matters most to reinforce is this surface here. So basically, in order to do that, we look and we say, okay, we have this top surface. The top surface of the part can be reinforced with isotropic fill if we can fit it in, or concentric fill as much as we can fit. And then we can use concentric fill because concentric fill will basically sit right on the inside of the walls of the part for these little areas here. And that'll get us our kind of a surface reinforcement there. So that seems to be the critical thing, the critical area of this part where reinforcing provides the most actionable strength. Now, regardless of your loading, you really don't want to have what we call imbalanced fiber. So if I just reinforced the top of this part, the issue might be that the bottom of my part is weak. I only have one kind of region of fiber, and it's on kind of the top of the part. So the bottom of the part is still kind of bendy, and then might get some warping just because of the strength of the part and the way that the printing works. So you want to kind of balance your fiber around the center of mass of the part. And so in this case, the center of mass is a bit lower. So it makes sense for us to reinforce that lower face as well. Not only because there are some forces acting on it, but also because it will balance out that stuff on the top. So we have a region on the top and the region on the bottom, which makes us relatively symmetric about the center of mass of that part. And yeah, so once we get here, now we have kind of this like strong, fully reinforced part. We have a good theory. And then the last step is to kind of go into the details and make sure that my part's being reinforced properly. And so as I mentioned here, as I mentioned earlier, it looks like it is. So our top two faces here, these ones, are being reinforced with this isotropic fill. Our contoured region has concentric fill, which means basically that entire wall will be reinforced. And then our bottom of the part, to kind of balance it out, has a region of isotropic fill just to give us that symmetry as well. So once you've kind of completed that fiber pathing, then you say, okay, I'm going to print this part and see how it goes. One common question we get kind of pre-answering this is how much fiber should I put in my part? And because our most 3D printed parts don't work super well with FEA at this time, it's really hard to give you a specific thing based on your loading conditions. So the best answer we can usually give is find your loading conditions, put fiber where you believe it to matter the most, and then because printing is a relatively cheap process against normal fabrication, don't be afraid to test your parts. And so that's kind of a really key early way to kind of block to get over, is because you can just print this out and then immediately test it. It's kind of a more actionable way of seeing if your reinforcement is good than doing something theoretical. The last thing I want to say is just kind of some key takeaways about just this presentation. So the first one is that the continuous fiber enables something really powerful, which is printing parts, which is a generally pretty easy process at near the strength of metal or the strength of metal. So you're superseding the strength of plastic. So when you're looking for parts that need to be that strong, that need to be that good, this is kind of your answer. The second one is that selective and intelligent fiber use is critical to the success of your prints. And so what I mean by that is that I like to say when I talk to prospective customers, like if you wanted to design a part that will make a Mark IV 3D printer fail, like you absolutely can. There's 100% chance that you can design something that our printer won't work on. That being said, it's exactly that's the same thing as saying I can design something that the Bridgeport mill downstairs in our shop will also fail on. So it's a process you have to kind of think about critically. So designing stuff for additive manufacturing is just a subset of designing stuff for manufacturing. So using that fiber critically in places it's critical and not overusing it is a really important step. And then the last thing is this webinar really focused a bunch on kind of the tools you can use and the knobs you can turn to do stuff. But the most important knob you can turn is the way you design your parts. So when we see prospective customers come into kind of our funnel, they talk to our subject matter experts, our people who kind of understand the process. we see parts often that are just not designed for additive manufacturing because they were previously subtractive manufactured, formed, any one of many processes that has very different requirements. So especially with this fiber printing, where the strength is anisotropic or kind of imbalanced across different orientations, you want to be super you're going to be super smart and critical about how you're designing the part, with the idea that you're going to put fiber in it. So parts that are designed earlier, or kind of designed with the intent of being reinforced with fiber, are generally the best parts. So then when if you start thinking about, say, print orientation, how you're going to print it, even before you even start CADing the part, that'll help you inform where you can put fiber in, where the part's going to be strong, and how you can kind of game the system there. Yeah, and so I guess with that, that's the end of kind of my formal presentation. And Andrew said we had some questions. Haven't done this with Saratech before, but I'm happy to answer any questions about the process, about Markforged printers, about 3D printing in general. But yeah, thanks so much for your time today. And yeah, open up for
Great job.
questions.
Thank you so much, Daniel. Great job. Yep. So if you haven't already answered these, what fibers can you reinforce parts with, and how strong are the fibers?
Sure. So kind of a cool question. First one, so we have 4 continuous fibers we work with. We mentioned kind of carbon fiber the most heavily because it's the most well-known of them. So we have continuous carbon fiber. We have 2 types of fiberglass. One is kind of our basic fiberglass, and then one is a high-strength, high-temperature fiberglass that has a higher heat deflection temperature, works better in that kind of environment. And then the last one is Kevlar, which is really good because you can kind of it takes abuse really well. Well, a lot of other fibers might snap. Kevlar just kind of like bends and it might deform, but it will not break. So it's super durable. In terms of how strong they are, as we said, if you really fill a part with fiber, it can get to that near aluminum strength. But most parts realistically are kind of in this area between aluminum and kind of the strongest of plastics, where they're stronger than any plastic. They're not quite at that metal level, but they're pretty strong.
Awesome. And then one more. Can you reinforce fibers in the Z-axis?
Yeah, so that's one where it's tricky. So as I kind of mentioned, you can't. The hardest part, the weakness of the process is that it is of 3D printing generally, is that it's anisotropic, or basically parts don't behave the same if you pull them in every direction. And the particular weakness of 3D printed parts is in the Z-axis. So the answer to this question is no, we cannot. So when you're thinking about it, you really have to be kind of like mindful of what the Z-axis is, because you can't reinforce it. And because the parts get so much stronger in the X and Y axis, it's actually the ratio of strength between the XY axis and the Z axis is even greater. So you do want to be careful with that. You want to make sure that since you can't do it, you want to design around that and make sure that the forces are minimized in that Z axis if you can manage it.
And it looks like we have another one. Can you use graphene? Graf, or I'm sorry, PHENE.
So we cannot use graphene so far as in this way. Graphene is, I'm not a composites expert. So far as I know, graphene is basically just like really, really thin tubes of carbon fiber. So continuous carbon fiber is graphene-esque. They're all types of they're all types of carbon. But yeah, we don't call our stuff graphene by any means, and it is not graphene. But the continuous carbon fiber is basically long strands of fiber that are unidirectionally strong in kind of the tension axis, and then by orienting them around the parts get super strong in multiple axes.
Okay, and I think that's all the questions we have, unless anyone else does. You are welcome to send us questions as well right after the session is over. We will have a quick survey, should only take you about 30 seconds. Let us know how we did today. Let us know about any questions you may have, any way that we can follow up with you. And then also let us know if you have any suggestions for future sessions. If you really like today's session, but you want to hear more, or maybe we didn't cover something that you want to hear about, please just let us know. Like I said, we meet here twice a month. So our next session will be on April 4th, and we're going to be talking about some new features in NX Cam with Mark Anderson. If you use NX Cam, you've called our support line before, you've probably spoken with Mark. So make sure that you join us there. And even if you can't join us, you can go ahead and register on our website and we'll send the recording out to you as always. Next slide. Are we stuck? That's
Oh,
okay.
I can turn my stop sharing.
Oh, no, that's okay. Yeah, I'm not sure why it sucked, but that's okay. Anyway, if you're make sure that you go and follow us on YouTube and make sure that you subscribe to our channel. And that way, we post a lot of short videos as well, not just 30-minute videos. So we do post shorter videos as well. So make sure you just go check out our YouTube channel. We have lots of awesome information there. And that is about it. Thank you again, Daniel.
Yeah, thanks for your time, guys. Hope you had a great, hope you have a great rest of your Thursday.
Awesome. Thank you. Talk to you all soon.